In this tutorial, we'll go through some of the commonly used components in the transform menu, and I'll provide some practical examples generally aimed at various types of fabrication and rationalization of geometry. So to begin with, let's have a look at some affine transformations. So affine transformations preserve parallel edges in geometry. So this toolbar or this menu just contains components like scaling, non-uniform scaling, projecting, and this orient component, which is really like scaling as well. So to begin with, let's have a look at the project component and talk a little bit about why you might want to use it. So project has two inputs, quite a simple component: the geometry that you want to project and the projection plane. So as far as I know, you can project just about any type of geometry. Let's try projecting a surface and see what happens. I'm going to project it to the XY plane. And you get a 2D representation of that surface in this plane. And the direction that it projects in is the Z-axis of whatever plane you provide here. So let's have a look at projecting it to the YZ. Or the XY. So it's just creating, or the XZ, a 2D representation of that geometry. Now that's occasionally quite useful for producing two-dimensional panels. So for instance, if we wanted to contour this surface and then produce some geometry for fabrication, we could use project to project the 2D curves on the surface back down to the XY plane and then loft between them to create 2D panels. So let's use a contour component, which we'll look at in a bit more detail in another tutorial. Contour. I'm going to contour my surface. I'm going to use the origin as my start point. I'm going to use the x-axis as my normal direction and a handy little slider for the size of my contours. So it's a pretty convenient component, and we'll look at some of these other intersection components in a different tutorial. So how do we take those 2D curves and use them to produce 2D panels for fabrication? Well, if we project them to the XY plane, as we did before, suddenly we get nice straight lines directly underneath our curves on the surface from our contour. Then we can use a loft to loft between our curve on the surface and our projected curve. So that conveniently creates these 2D panels. Now we're going to jump around a little bit between these toolbars because sometimes you need to combine multiple transformation components to achieve a certain effect. So let's have a look in the Euclidean menu. Now the Euclidean menu preserves scale as well as parallel lines between or within geometry. So it's basically used for moving things, orienting things, and rotating things. So this keeps the shape of your geometry and size. So what we're going to do is we're going to take each one of these now two-dimensional panels from our contours, and we're going to use one of these components to lay them out parametrically in a grid. Speeds up the fabrication process. So the alternative would have been baking these things, getting stuck into Rhino, and one by one moving them, rotating them, and labeling them. Okay, so you can do that. Imagine if we had sort of 100 contours, it starts taking quite a long time. I'm going to undo before the bake. Instead, what we can do is we can use an orient component to reorient all of these sections, which are currently oriented in these shifted XZ planes, to lay them out flat onto our Rhino construction plane. It's a simple component as well, just like this project component. Just takes some geometry to orient. So let's use our lofted sections. It asks for an initial plane. So this is sort of like a reference plane telling this component how to match up the initial condition to the target condition. So if we can use some component to find a reference plane which sits within each one of these lofted surfaces and describes the current orientation of the surface, we can use that as our reference plane. Luckily there's a component that does that. In the surface menu we can use a component that just tells us or tests a surface for planarity, which means it checks how curvy a surface is. So we'll use that, and it outputs planes which best approximate the plane of a surface. So you can see already it's pretty neatly creating a reference plane for us on each one of these surfaces. So let's use those reference planes, which is this input, or this output, sorry, as the initial plane, or the A input to our orient component. Now we need to lay them out flat. Now we could just use the XY plane, which will lay them all out flat on this Rhino construction plane for us, but they're all overlapping, so we'd still need to get into Rhino and move them so that they're not overlapping, so we can send them off to the laser cutter. So instead what we want to somehow do is, instead of supplying one origin for this plane here, we want to supply origin points which exist in a grid so that these things don't overlap. Now I'm just going to flatten this, and you'll learn what flattening does next week. Okay, so we'll make a grid. Let's make a square grid, and by default it's about that big. Now what I also want to do is find points in the center of all of these cells, because by default it outputs corner points and grid cells, though we could just use the corner points, it doesn't matter too much. And it outputs them in this data structure, so that's these rows of funny symbols here, which we also want to get rid of, so we're going to flatten this as well. Now the main point of this tutorial really is to show you what the orient component does within the context of a slightly more complex example. So all of these little nitty-gritty parts to the tutorial you'll understand in more detail through the rest of the course, but for now we just want to watch and see how we use the orient component in context. So I'm creating a list at the moment of 36 points. If I plug that into our XY plane, it's going to create 36 XY planes at each one of these points. So let's just make the grid a little bit larger so we can change the size of the grid cells. Let's make them more like that big. Okay, we've got no overlap anymore. But now we have a problem because we've got 19 surfaces, but we're creating 36 points for these surfaces to be oriented to. So we can change the size of our grid. Now we have 30 points at the corners. Let's turn it down again. Now we have 25. Now we have 20. So 19 and 20 is pretty close. There's no parametric link here yet. So if I changed the number of contours, I'd then have to go and change these sliders as well. So that's a little bit irritating. But in the tutorial which you can download, or this Grasshopper file that matches this tutorial that you can download, there's a method in there for parametrically linking how many grid cells you need here. So lastly, we can use a component to just get rid of the extra grid cells, because what happens by default, and again next week you'll learn a bit more about this, is that when we're supplying too many planes, so an uneven amount of target planes compared to our reference planes, it just copies the last plane again. So we can use a short list component to trim this longer list here, and that'll get rid of the extra one. And then if we make this grid much larger, it's still going to be trimming off the extras. So lastly, we can also, just for convenience, use a point list component to label, and we'll hide these planes, to label all of our individual pieces of geometry. Now let's look at another use for the orient component. So one use that I've just shown you is laying these components out into a 2D plane for ease of fabrication, saves you lots of time. Another use is to approximate curvilinear geometries like this surface here using 2D elements. So let's have a look at that. I'm going to get rid of some of this definition, go back to just my surface with the contours, and we're going to orient a geometry onto these curves. So first of all, let's divide the curves. And if you've watched the curve menu tutorial, you'll be familiar with this component. And then let's use this information that we have here to create some planes. So I'm going to use a plane component. I'm going to create a plane at that point. And that'll actually do for now. Let's start orienting something. We'll go back to our transform toolbar, Euclidean, orient. Now I've drawn a rectangle around the origin here, and this is going to be my component. I'm going to reference it using a geometry parameter, which is in here somewhere. So this parameter just stores all types of geometry. Plug that into our G input. Our target plane is going to be all of these planes which I just made on the curves. And by default, the orient component uses this XY plane here, so we don't need to make one for our reference plane. And now let's hide some of this stuff. So you see what that's done is it's copied this component onto these curves. And we have some control over how it's doing this, so the component is always positioned so that the middle, or the center point, centroid if you like, of that component is on the curve. Those planes that we created are already and always XY planes, so the component has minimal rotation, it just has a changing position, which makes it really easy to fabricate. So you can imagine laser cutting those lofted sections that we just created, producing a tiny little notch and fitting these panels onto the surface. We could also start adding some degrees of freedom to these components by adding some more information to these planes that we're creating. So far we've only provided it with an origin point, but if we add a variable y-axis, you can see all of those planes change, and now our components are also going to follow that curve. So we can start approximating the geometry of that surface using these little overlapping panels. Now that we have our oriented geometry, we can use some of the other transform components to begin manipulating that geometry relative to some other information in our parametric model. So if we go back to the affine menu, one interesting component is scale NU, which stands for non-uniform. which just means that we can scale our geometry with different factors in the X, Y, and Z axes. So let's create one of those. It takes quite a few inputs. We need some geometry to scale. So let's scale our oriented geometry here. It needs a plane to perform the scaling in. So let's use the same plane that we used to orient this geometry. And meanwhile we'll hide the orient. And then we have these three scaling factors, which by default are just 1. Now if we hook up a slider to one of these, we can scale all of the geometry non-uniformly. So now we're scaling in X and Y. And the example that I'm going to quickly knock together is just to show how we can scale each one of these little components relative to their location or proximity to a point. So to do so, and again all of this stuff is covered in later tutorials, but it's just to make a practical example of when you'd more likely use this component. We're going to find the distance from our oriented plane to a point. Then we're going to remap those numbers so that they have a real scale, otherwise all these distances are going to be quite large. We can't use that as a scale factor, or we have extreme distortion. So I'm going to remap those values to something more usable. There we go. So these values, or these distances to this point, have now been remapped to some figure between 0 and 1. So the closest component to the point is going to be scaled to 0 in the x-axis, and then the further away these components get, they'll be scaled more and more like 1 unit. So now we have components oriented along curves, and every component varies in its properties relative to some control object in our model. We can also use some of these transform components to create simple strip geometry. So I'm going to show you that now. Delete this old model so that we're working just with the contours on our surface again. And let's have a look at one of the simplest Grasshopper components, which is just move. So move has two inputs, a geometry that you want to move, so let's move our contours, and a translation vector, so the direction and the magnitude that you want to move in. So let's just use unit x vector, which is going to move all of our contours 1 unit in the x direction. And then we can simply loft between our contour and the moved contour to create these strips. And it's essentially the same functionality as the extrude command. So these strips, because the move doesn't distort our geometry at all, we know are going to be developable, which means they can be unrolled and fabricated from flat material. So another example, as we move through these menus, is to have a look in this morph menu and talk about box morph. Now all of the components in the morph menu do distort your geometry, so you can plug in a nice polysurface consisting of entirely planar faces, put it through a box morph, and it'll end up as twisted, complex surfaces that maybe can't be fabricated out of 2D material anymore. So you have to be quite careful when you're using these components. They're good for producing representations and not so good for producing fabricatable geometry. But if you stick with triangulated meshes, mesh triangles can never be twisted into strange shapes. They're always going to be triangular, they're always going to be made out of these flat faces. Then you can use these morph components more effectively. So the example that I'm going to show you here is we'll have a go at recreating Co-op Himmelblau's, one of their new buildings, very diagrammatically. So we'll begin with lofting some curves. So I've got some funky looking curves here. We'll loft them together. Might delete this stuff up here. We've got a bit more room. And we've got a fairly complex looking surface. Now if we go to our box morph in the morph menu, let's drop this box morph object down. So it takes a couple of inputs: a base geometry, which is the thing we want to morph, a reference box, which is kind of like the reference plane in the orient component, and a target box, like the target plane in the orient component. So it's just like a 3D orient, except unlike orient, this will distort your geometry. So the geometry we want to morph, I've made this little component here, which is a mesh. So to remind us that it's a mesh, we'll reference it in as one. And that's going to be our geometry. Now our reference box, we can just plug our mesh in, and Grasshopper is going to automatically fit a box around it. The smallest possible bounding box, XY aligned bounding box. Now we need our target boxes. So a bit like with the orient chute, we've got to find a way to make boxes on this surface. So let's go up to this morph menu, and you're going to find that there's a convenient surface box component. Now the surface box component is very convenient because all of your boxes on the surface share faces and edges, so you'll get a nice continuous blend of components across the surface. You won't have any gaps. So let's use that one. It asks for a base surface, so we use our loft. It asks for a surface domain, and it asks for a height. Now, creating one single domain, that's pretty easy. You can go up into the maths component, have a look in this domain list, and we've got a whole bunch. But I'm going to start skipping over this part of the tube quite quickly so that we can focus on the box morph. I'm going to create a two-dimensional domain, and then I'm going to divide that domain up into smaller chunks, and I'm going to use those to create these boxes on the surface. So you can see at the moment they're all the same height. They've got a height of 1. And that just lets us tone it down a little bit more. Now what we'd really like, again, just like with the last tutorial where we were scaling those components across the oriented planes, it'd be nice to have some variation in these boxes as well. So for now, I'm going to evaluate my surface. No, I'm not. I'm going to divide my surface. Into the same number of boxes that we have. So let's say we have 10 and 10 minus 1. These are expressions which let me perform little maths functions on the input. And hopefully we now have 100 points and 100 boxes. Now we can play with this normal vector, which is what I'm going to do. And I'm just going to decompose it so that we can play with, just say, the z component of that vector. So a normal, as you should already know from earlier tutorials, is a vector pointing perpendicularly out from the surface. So if we evaluate its Z component, the more horizontal our surface is, the larger that Z component should be. So you'll see that now we've got some really big boxes as the surface becomes more horizontal. So that's enough variation for the sake of this tutorial. So we've got all of our target boxes now, pump them into this T input, and suddenly we have our components distributed across this surface. Now we might just quickly go over some of these mesh tools again to prove that these have not been distorted. So we can grab these face boundaries of all of our morphed meshes, and to double check we can plug them into a planar surface. Planar. There we go. And the component still generates planar surfaces for us. Now, in your own time, if you want to try using the box morph on regular old NURBS geometry, you'll be able to see how it distorts objects. You might also want to experiment with generating different variation in your surface boxes, and of course you'll want to have a look at some of these other utilities up here. I haven't gone over the utility components in this tutorial, but they're included in the downloadable Grasshopper definition. And they're essentially convenience components for combining geometry into groups and combining transformations, just so you don't have to copy paste lots of transforms all over your definition. Some other interesting morphing components, I don't use them too often because they tend to be slow and they distort your geometry, but the spatial deform can produce some pretty interesting results. And obviously you use components like rotate and mirror all the time in your definitions, so have a look at those.